Okay, serious question? How do you ensure part-level traceability across manufacturing processes that destroy, cover, or erase traditional identifiers? In every mission-critical system, vehicles are powered by thousands of critical and safety parts. These parts go through extreme and complex manufacturing processes: casting, coating, galvanization, cataphoresis, electroplating, painting, heat treatment, shot blasting, and acid baths. But here's the problem. Traditional 2D identifiers weren't designed to survive these processes. They were only meant to identify the final product during assembly or once manufacturing is complete before shipping with external packaging. During production, these codes often become unreadable because they rely on just one fragile principle: cell contrast. Optical challenges, surface contamination, and harsh industrial processes such as heat treatment, shot blasting, e-coating, painting, or galvanization can erase or permanently cover a code. CDOT code is engineered for the manufacturing processes. It doesn't rely on visual contrast. Instead, CDOT is decoded through Cosmedau's patented Fourier transform-based signal analysis. Rather than interpreting visual pixel patterns, CDOT encodes information into harmonic dot structures. These structures produce signature frequency peaks across 62 reference points in the frequency domain. Even if the physical code is partially damaged, the 3 to 4 unique frequency reference points are enough to fully reconstruct the original unique ID. A 5mm squared CDOT code stores over 1013 unique IDs and 520 characters, is mathematically unique, and is physically bound to the marked surface, making it impossible to clone or reproduce. In bottle tanks, chassis parts, and other critical components, CDOT codes stay scannable after extreme treatments such as shot blasting, heat treatment, and military paint. In aluminum EV battery housings and covers, CDOT is applied during die casting, a process that produces rough, reflective finishes. Even after heat treatment, the code remains fully readable. Gears and disc brakes undergo heat treatment, phosphate coating, and blasting, yet CDOT remains legible. Crankshafts, base oil, and machining residue, but CDOT is still readable without cleaning, directly in production. In engine blocks, CDOT is applied while the cast iron is still very hot, and it stays readable after heat treatment. On engine cradles and subframes, CDOT works even after e-coating, where traditional codes become unreadable. Sand core molds are marked before casting, transferring the code into the metal and proving that traceability can start at the sand core stage. In cast iron brake parts, CDOT is applied on sand molds before metal parring. When the casting solidifies, the code is already embedded in the iron and ready to be scanned. Powder-coated and enameled parts keep readable CDOT codes even after curing in the furnace. On outer body panels, thin steel sheets retain traceability after forming and full paint when CDOT is applied before painting. On steel billets, codes can be applied at 1292 degrees, where data matrix codes constantly fail. CDOT codes remain readable and survive oxidation and scaling. On steel profiles, CDOT is marked before chemical treatments begin. Once applied, the code survives acid baths without losing integrity. Even as layers of protective galvanization form, the original CDOT code remains readable. On steel pipes, CDOT resists 2x/3x cold drawing, staying intact as the pipe stretches. On other steel pipelines, CDOT remains readable through shot blasting and heat treatment. CDOT code, built for industry. Visit thecosmodot.com.